The 3D inverse solver is an iterative, inviscid potential flow solver which starts from a defined flow field and then builds a geometry around that flow in order to perfectly sustain the field. The blade shape is defined by a function, f. The solver uses the kinematic boundary condition, which dictates that the flow must be tangent to the blade surface. The process iterates as follows. Initial guess. An initial blade shape is assumed represented by a sheet of discrete vortices, whose strength is directly related to the specified loading. Velocity calculation. The solver computes the 3D flow field based on the current shape and the prescribed RV theta. Blade evolution. If the calculated velocity is not tangent to the surface, the blade coordinates are updated. This ensures that the blade wraps itself around the prescribed flow field. Convergence. This continues until the blade shape stabilizes, meaning the geometry perfectly sustains the requested swirl distribution. To produce a 3D blade with specific thickness, the inverse solver uses two types of sources in the potential flow field: vortex sheets, which represent the mean camber line and the loading, and source sheets, which give the blade volume, with a distribution of sources and sinks placed along the camber surface. When considering the blade stacking, we know that conventional lean increases the profile loss at the midspan region. The 3D inverse design method automatically recambers the blade for any complex stacking. Streamwise and spanwise work distribution is maintained, so we can suppress end wall and mid-passage loss by applying complex stacking with no loss of performance.